So in this video, we're going to take another look at linear systems of equations and think of another way to interpret what's going on. So let's start by writing again our 2x2 linear system of equations where we have two variables, let's call them x1 and x2, and we have coefficients that multiply these two variables, a11, and this is plus a12 equals some value we call b2. B1. And so this is our equation 1, and we're also going to have equation 2 where we're going to have coefficient a21 times x1 plus a22 times x2, and this will be equal to our coefficient, our number b2. Right, so again, this is our equation 1, and this is our equation 2, and the unknowns are x1 and x2 in both equations, and the values a11, a12, a21, a22, and b1 and b2 are known. Right, so of course we have learned how to think about this linear system as a matrix A applied to a vector x equals another, made a mistake, A applied to matrix to vector x equals another vector b. Right, so where again the definitions are that A will be our matrix of a11, a21, a12, a22. Our vector x will be x1 and x2, and our vector b will be b1 and b2. So this is our standard setup, and in the case when the vector x is a vector of unknowns, right, we know the matrix A and we know vector B, so we have had this drawing in a video before where we can take, for example, let's draw, I don't know, vector B over here. This is going to be our vector B, and we have our matrix A that will map some other vector x that a priori we don't know. Maybe this other vector x is over here, right? But this vector is unknown, and the matrix A is the operation that takes you from x to b. So solving a linear system of equations such as written here, another way to say this is that we are seeking for what would have been the vector x that if I applied A to, I would have ended up with vector b. Right, so this interpretation we already saw before, and of course I forgot to draw our axes here. Our axes are x1, and x2. Here's another way to think of this, and we're going to look at this linear system of equations again. So for example, if we look at over here, we can look at the columns of this matrix, A, right? The columns or equivalent, these are the numbers that correspond to the same thing. We see that these two numbers here are multiplied by the same coefficient, x1. Right? And likewise, this is another column which is represented here, and they're multiplied by the same numbers, x2. So another way to interpret what's going on here is that we are adding two vectors, and I'll call these two vectors a11, a21. We're taking a linear combination of these two columns of the matrix A. And this is our vector b1, b2. right? So I mean, we can name these whatever we would like to name them. For example, let's take the blue color here. I'm going to rename this vector here v1, for example, and I'm going to rename this vector v2. So another way to write the equation above is that we have v1 x1 plus v2 x2 equals our vector b. So here again is our vector b from our previous example. I'll try to draw the same vector. And, you know, in this case, I don't know, you know, we didn't plug any value, so I'm making up what the vectors v1 and v2 would be. One way that I can make this up is I can just write this vector v1 to be aligned with the x-axis. So this is v1, and this is v2 is aligned with the y-axis. So another way to interpret this linear system of equations written over here is writing it in such a way to see that we're asking, when we're solving the linear system equation, we're asking for what are the coefficients of this linear combination of the column vectors of A, such that when I perform this specific linear combination, I get exactly vector B. So it's like I'm trying to represent vector B with a linear combination of the column space, the columns of A, right? And that's one way to have a geometric view of what's going on with a linear system, right? Which leads us to also have a good intuition and a good interpretation for when does the linear system have a solution and when it perhaps doesn't have a solution, right? If we have a situation where it's not possible to add vectors, vector v2 and v1 to make up the vector b, then the linear system doesn't have a solution, right? So for example, if v2 in this case that is drawn here was drawn on this axis instead, then there will be no y component to make up for the y component of b. And in that case, you could not have the solution to that linear system, right? That's another way to say that the lines of these, the lines corresponding to these equations are parallel. Likewise, for example, let's say we have a different linear system of equations, and let me write this way now. We have a11 times x1 plus a12 times x2, and now I'm going to add a third one, a13 times x3, and that's equal to our b1. And we're going to say here a21 x1 plus a22 x2 plus a23 x3 equals b2. Here we have a31 x1 plus a32 x2 plus a33 x3 equals b3. We do the same business again, right? We view this as one vector. This is this as another vector. This is another vector, right? So I'm going to do the same substitution that I did above. So we're going to call this v1. This is v2. And this is v3, right? This is our old vector b. So I can write this specific linear combination as v1 x1 plus v2 x2 plus v3 x3 equals the vector b, right? So let me draw some possibilities here for what v1, v2, v3 can be, right? These are given for, they're dictated for by whatever values are in the matrix, but I'll draw the same ones as I had before. v1, This is V2. And I don't know, I'll choose a V3 this way. Right? And once again, our vector B is over here. Well, you know, as we already noticed from the example above, it was already possible for me to form vector B by linear combinations of vector V2 and V1. That was already possible. So when we add a third one, we can see that now it's actually possible to form this vector B, which again, I forgot to draw, but vector B is here. It's possible to draw this vector B by combining either V1 and V3, or V1 and V2, or any other linear combination. So here we can see that we have an infinite number of solutions, right? So in this case, I just thought to bring this up so that we can learn how to think of this, the so-called column space of our linear system, right? And the column space, what we refer is to the set of all possible linear combinations of vector V1, V2, and V3. That's what we call the span of these three vectors, right? And for example, and we can start thinking of this system of linear equations as a transformation or a map that maps, you know, in this case, R3 to R3, right? Or in our case here, sorry, I marked R3 to R2, right? So we have, we're drawing in 2 dimensions, so I have to erase. Right? And the column space of the matrix A is informative as to whether we have one unique solution, no solution, or multiple solutions.